Hello students, and welcome back to another geometry video. You know what to do. Pause the video, try these problems in your notes, and then unpause it to do them with me. So, we noticed that we have three parts to this question. We have an A, B, and a C. So let's start with part A. We have that ZX is the perpendicular bisector, which means that for part A, I can say that WX is congruent to XY because that's what it means to be a perpendicular bisector. And YZ is 13.75. Find WZ. Well, that's easy. If this is the perpendicular bisector, I know that any point on the perpendicular bisector is equidistant from either endpoint. So, WZ is 13.75. Ta-da! Alright, on to part B. So let's erase all of this. Move on to part B. ZX is the perpendicular bisector. Okay, so we can draw these lines again. And, whoops. There we go. Now I'll erase all this. Alright. ZX is the perpendicular bisector, so we can draw these again. WZ is 4n minus 13, and YZ is n plus 17. Find YZ. Well, YZ is n plus 17. We just need to figure out what n is. So let me get a different color, and we're going to do 4n minus 13 equals n plus 17. We'll subtract n from both sides. 3n minus 13 equals 17. Add 13 to both sides. 3n equals 30. And hey, divide by 3. That gives us that n is 10. So, if I plug in 10 for n, we have 10 plus 17, which is 27. So YZ is equal to 27. All right, and part C. So let me erase part B. For part C, we know, or we want WX. So find WX when YZ is 20.5, WY is 14.8. Oh, whoops, WY, not XY. WY is 14.8, and YZ is 20.5. Hey, these are the same. 20.5 and 20.5, those are the same. Hey, which means that Z lies on the perpendicular bisector. So we know that WX, whatever it is, we'll call it X, is the same as XY. I know that the whole thing is 14.8, so WX is 14.8 divided by 2. It's half of 14.8. Whoops, 14.8, which is 7.4. 7.4, and we got that by doing 14.8 divided by 2. Ta-da! Wonderful. Beautiful review of last time. Now, let's see what we have for today. Today we are continuing with chapter 6. We are in 6.2 now, talking about bisectors of triangles. So now we're throwing triangles into the mix. So, what conjectures can you make about the perpendicular bisectors and the angle bisectors of a triangle? So we're doing still working with the perpendicular bisectors and angle bisectors from 6.1, but now we're adding triangles into the mix. So, our learning target is that you know what the circumcenter and incenter of a triangle is, or are. What are the circumcenter and incenter of a triangle? So our success criteria is that you can find circumcenters and use properties of incenters. Finding incenters is difficult, so we're not going to do that in this video. Maybe in a future one. Stay tuned. So, I can find circumcenters and use properties of incenters. So, first, we're going to talk about circumcenters, then we're going to talk about incenters. So there's kind of going to be two parts to this video, just like last time with the perpendicular bisectors and the angle bisectors. So first up, we need to know what are circumcenter and incenters. What is a circumcenter? And in order to talk about that, we need to talk about what the word concurrent means and what a point of concurrency is. So first, if we look on the left, concurrent, and we're going to hear this word throughout 6.2 and 6.3. 3 or more lines, rays, or segments that intersect in the same point. So 3 or more, that's important. 3 or more lines, segments, rays that intersect at the same point. So in this example, we have that lines J, K, and L are concurrent because they all intersect at point P. And that point P we call the point of concurrency. The point of concurrency is the point of intersection. It's where concurrent lines, rays, and segments cross. So if lines are concurrent, the point where they cross is the point of concurrency. Now, this is important because we're going to talk about 3 points of concurrency. There are 4 points of concurrency within a triangle. Right now, we're only going to talk about 3 of them because one of them isn't very interesting. It doesn't have a lot of properties to it. It's interesting for reasons, but it doesn't have a lot of applications. So we're not going to talk about that one right now. But one point of concurrency is the circumcenter. Hey, circumcenters and incenters are both points of concurrency within a triangle. The circumcenter is made by the 3 perpendicular bisectors. So the circumcenter is where the perpendicular bisectors of a triangle cross. So, notice these blue lines are all of the perpendicular bisectors, right? Because we can see it's cutting the sides in half and it's at a right angle. That's what it means to be a perpendicular bisector, is to cut it in half at a right angle. So, point P, let me get a different color. Point P is the circumcenter. It's where all of the perpendicular bisectors cross. So, where all the perpendicular bisectors cross in a triangle. So you take the triangle's sides, you make the perpendicular bisectors, and wherever they cross is the circumcenter. Now, great. I know what a circumcenter is. Why the heck do I care about a circumcenter? Well, because of this awesome theorem, the circumcenter of a triangle is equidistant from the vertices. So if you have 3 points, you have A, B, and C, and you want to know where is the middle of these points? Where is the exact middle of all of these points? What point is the same distance away from all of these corners? That's the circumcenter. So if you can construct the circumcenter, you know where the middle, or what point is exactly the same distance away from all of these corners. So that's why the circumcenter is helpful. And yeah, there are many applications of this that we won't get into today for the sake of time, but they do exist. So, the circumcenter of a triangle is equidistant from the vertices. So if you make the circumcenter, you can draw these purple lines. You can say that I know that from the circumcenter to the corners of the triangle, to the vertices of the triangle, are all the same. So if these blue lines are perpendicular bisectors, yada yada, then PA, PB, and PC are all equal. The distance from the circumcenter to every corner is the same. Awesome. Beautiful. Now, some very interesting information about the circumcenter. The circumcenter is not always inside of the triangle. You would think that sometimes it's inside, or that it would always be in the triangle, but it's not, only sometimes. If we have an acute triangle, remember we learned about the types of triangles in 5.1, how to classify acute, right, and obtuse. If we have an acute triangle, the circumcenter is inside. If we have a right triangle, the circumcenter is on. It is on the edge. It is on the hypotenuse of the triangle. And if we have an obtuse triangle, the circumcenter is actually outside of the triangle. And that makes sense, because if I need to be the same distance away, if I'm in the triangle, I'm going to be way closer to this vertex than I am to that vertex. So it makes sense that it would be on the outside. So, this is very interesting information, and it's going to help us with our next example. Finding the circumcenter of a triangle. So, now they're going to give us the coordinates of the vertices of a triangle. We have to make the circumcenter. So that can sound a little intimidating, but I'm going to walk you through each step. Step 1, graph the triangle. Whoops, that doesn't look like a triangle. There we go. The triangle. There we go. So 0, 3 is point A. 0, -1 is point B, and 6, -1 is point C. So we'll connect these dots. And there we go. There's our triangle. Hey! What kind of triangle is this? It's a right triangle. I know, because vertical and horizontal lines are perpendicular. So this is a right triangle, which means that our circumcenter is going to be on the hypotenuse. I know that my circumcenter is going to be somewhere on this edge, wherever looks like the middle. Somewhere on the hypotenuse, that is where my circumcenter will be. But I can't just guess. Like, I can't just say, oh, I think it's here or something. After I graph the triangle, I need to graph the perpendicular bisectors of each side. And now, when we say of each side, you really only need to do 2. Because we know that the third bisector will intersect where the other 2 do. We know that wherever the 2 bisectors are, the third one is gonna bisect there as well. So we actually only need to find 2 of them. And I'm gonna do that in purple. So graph the perpendicular bisectors. So the easiest sides to do, since we only need to do 2 of them, the third one will go through that same point as well. Let's pick the horizontal and vertical lines, because trying to do this slanty one, the diagonal one, is going to be a little difficult. So, how do I graph a perpendicular bisector? Well, remember that a bisector is the middle of a side. So we just need to find the midpoint of this side down here. Now, we can use the midpoint formula. You can totally do that from from chapter 1. You can totally do that. So we could take the coordinates of B and the coordinates of C and do, 0 plus 6 over 2, -1 plus -1 over 2. We can do that. Or we can just count the boxes. There's 1, 2, 3, 4, 5, 6. Half of 6 is 3. So there should be 3 boxes on this side, 3 boxes on this side. Boom. There's the midpoint. Ha ha ha! Speed strats. Okay. Now, perpendicular, remember, vertical lines are perpendicular to horizontal lines. So because side BC is a horizontal line, we can just draw a vertical line straight through this. And we know that it's perpendicular. Because vertical lines are perpendicular to horizontal lines. So there's one of our perpendicular bisectors. Let's do the same thing with side AB. So I have 1, 2, 3, 4, which means that 2 is going to be the midpoint. If I have 2 boxes on either side, I am the same distance away from either endpoint, and that's what a bisector does. Now I just need it to be perpendicular. So again, because this line is vertical, I'm going to draw a horizontal line, and that is my perpendicular bisector. Now, I only need 3 of them. Or excuse me, I only need 2 of them, because if I draw a third one, we'll see that, oh gosh, something like that. But I don't need the third one. It goes through this point already. I know I have found where these lines cross, so I don't need to make a third one, because it's just going to go through the same point. So you can do the third one, by all means do the third one, but we don't have to. Step 3, we kind of already did step 3, but it's where do they cross? Where do the perpendicular bisectors cross? Because that is the circumcenter. So, where do they cross? We have 1, 2, 3 is the x-coordinate, and 1 is the y-coordinate. So the circumcenter is at 3, 1. Wonderful! Fantastic. Let's check and see if we were right. Step 1, graph ABC. Find equations for 2 perpendicular bisectors, since we don't need all 3 of them. Horizontal lines are perpendicular to vertical lines. Midpoints, perpendicular, yep, midpoints perpendicular. Find the point where they intersect at 3, 1. So the circumcenter is 3, 1. We were correct. Awesome. Alrighty. Next, we're going to talk about incenters. So in 6.1, we talked about perpendicular bisectors and angle bisectors. The circumcenter was created by perpendicular bisectors. The incenter is created by angle bisectors. It is the point of concurrency of the angle bisectors of a triangle. So, it is where the angle bisectors cross. So, notice how on each of our vertices or corners of the triangle, we have that the blue line splits it up into 2 congruent angles. So BP, AP, and CP are all angle bisectors, and the point where they meet, that is the incenter. Now, it's important to note that the incenter will always be inside of the triangle, because if I'm cutting an angle in half, any point on the angle bisector must lie inside. It must lie on the interior of the angle. So if I'm on the interior of this angle, and the interior of this angle, and the interior of this angle, well, I have to be inside of the triangle. I can't be on the exterior. So, the incenter will always be inside of the triangle. Okay, now why do I care about incenters? Great, I know what it is. It's where the angle bisectors cross. Beautiful. Why do I care? Well, there's another interesting theorem about incenters. The incenter of a triangle is equidistant from the sides of the triangle. So, with a circumcenter, we knew that the distance to each endpoint was the same. With the incenter, that is not true. With the incenter, the distance to each side is the same. And remember, when we say to each side, we're talking about the quickest line, the quickest way from the incenter to the side of the triangle, and that's always at a 90-degree angle. So, if you have the angle bisectors, and you know where they meet, then you know that from the incenter to each side of the triangle, that is the same distance. Now, in our next example, and our last example for today, we are not going to find the incenter. We're not going to graph and find the incenter, because graphing angle bisectors is much more difficult than graphing perpendicular bisectors. So instead, what we're going to do is we're going to take this theorem and we're going to see some problems that we can do to really understand this theorem, understand the properties of the incenter. So, example 3, using the incenter. Not finding the incenter, using the incenter of a triangle. So, in the figure shown, ND is 5x minus 1, and NE is 2x plus 11. The first part is find NF. Okay, so we want, let's not use red, everything's red in there. We want to find NF. Well, doesn't look like there's a lot to go off of here, but I'm going to get a different color. Notice I have the perpendicular bisectors of every corner. These red lines, BN, AN, and CN, these are the angle bisectors, which means that N is the incenter. N is the incenter because it is the point of concurrency of the angle bisectors. It is where the angle bisectors cross. So, hey, if I have all the angle bisectors, then I know the distance from the incenter to each of the sides is the same. So I know that ND, NE, and NF are all the same. So we know, and this is part A, for part A, we know that ND equals NE, which equals NF. So if I can find one of these, I know what NF is, because they're all the same. If one of them is 12, all of them are 12. If one of them is 8, all of them are 8. So, what do we know about these? I know ND is 5x minus 1. And I know NE is 2x plus 11. And I don't know anything about NF right now, other than that it is equal to these. So what we can do is we can solve 5x minus 1 equals 2x plus 11. We can solve this for x. And then I can plug x back in, find out what NE is. Oh, NF is the same thing. So, let's take it step by step. Solve for x. I'm going to subtract 2x from both sides. We get that 3x minus 1 is equal to 11. Add 1 to both sides. 3x is equal to 12. Divide by 3 on both sides. And x is equal to 4. There, that's NF. I'm done, right? No, that's x. That's not NF. So what I need to do now is I need to take this x and plug it in. 2 times 4 plus 11, that's 8 plus 11, which is 19. Okay, So, if NE is 19, that means that NF is 19. So all of these are equal to 19. And there's part A. Now part B. So I'm going to erase this for the sake of understanding what part B is asking. So let's do this in green again. Can NG be equal to 18? So NG is some random line right here. And they want to know, can it be 18? Well, that's a very interesting question. Because we know that NF is 19. So can NG be 18? Well, wait a minute. We said that NF, the whole reason that this is like perpendicular is because when we say the distance from the incenter to the side, we want the quickest distance, the shortest distance. So 19 needs to be the shortest distance. Well, if 19 is the shortest distance, how can 18 is smaller than 19? So that would mean that this is the shortest distance. But it can't be the shortest distance. So no. So for part B, no, it cannot be 18 because, BC means because 19 must be the shortest distance. And 18 is less than 19. So this is what we call a proof by contradiction. Now, we didn't write out enough detail for it to be a proof, but the thought process behind this is a proof by contradiction. So, you just did a proof by contradiction. Oh, in some form. Alrighty. Let's check and see if we were right. NF, okay, ND is equal to NE, which is equal to NF. Solve for X. Plug it in. ND and NE equals NF. So they're all 19. Perfect. And recall that the shortest distance between a point and a line is a perpendicular segment. Perpendicular segment is NF, which is 18, or which is 19. 18 less than 19. NG cannot be equal to 18. Yay! We were right. So, that's it for today. Now, think back to the learning target and the success criteria. Do you know what incenters and circumcenters are? If no, definitely go back, rewatch the definition and theorem portions of this video. Also, ask your teacher questions. Ask for help. There is nothing wrong with asking for help. I would not have any of my degrees without asking for help. I wouldn't have anything in this life really without asking for help. So it is okay to ask for help, and if you are not understanding, it means that it's time to ask for help. And if you're a 2, try the homework. Your next step is to try the homework. If you completely totally get it, you can try the homework, probably finish the homework, and help your friends, help your friends, classmates, family members, things like that. So, do you know what an incenter and a circumcenter are? Can you find incenters, and can you find circumcenters, and can you use properties of incenters? All right. Here, well, and there's some on the next page too. These are some practice problems. Let me get out of the way. There you go. Take a screenshot of that or pause it, whatever you want. These are some practice problems that you can do to practice the skills you have learned in this video, as well as these are some more problems that you can practice the skills in this video with. And, as always, let's end our video with a launch, shall we? Today's launch comes from Helen Keller, and she says, "Never bend your head. Always hold it high. Look the world straight in the eye. I like that that rhymes. Let's dissect each part of that. Never bend your head. Why not? This is bad? I shouldn't do this? No, no, no. What she means is typically when we say bend your head, you kind of think of like, like you're shy or like you're ashamed of something. And you have nothing to be ashamed of. You, in all of your, human mess that you are, we all make mistakes, we all make bad choices, but you are still enough just as you are, no matter what bad things you've done or what mistakes you've made. So you don't need to bend your head like you're ashamed. Hold your head high. You are enough. You've made mistakes, but you're getting better. You've done bad things, but you're working on not doing them anymore. Hold it high. Hold your head up high. Look the world straight in the eye. Look it straight in the eye like, I'm ready for you. I know the world is messy. It's rude sometimes, but I'm ready. I will look you straight in the eye, unafraid of what the world has for me, because I'm enough. I can take what this world has for me, and I'm gonna rock it. So, what Helen Keller is trying to say is have confidence. Have confidence. You don't have anything to be ashamed of. Have confidence and be ready for anything that the world throws at you. So, that is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day, and thanks for being here. Thanks for watching. Bye.